right, here we are once again at the physics video lecture. Physics 168, video lecture 14. Let's begin. We arrived at a great spot last time. I was going to talk about the Meteor Crater, and I sent you guys out to get some images. So I'm going to tackle that problem in some detail because it's rich. But I'll first list what we've accomplished so far, because we now have a fair amount of physics that we can use in order to talk about energy, right? The whole goal is to talk about energy, but we've had to do a pretty thorough trek through the subject matter. So let's go ahead and list our concepts and where we stand, and then we'll put together the Meteor Crater discussion. So if we're building things up from scratch, we had length and time. So first of all, we had unit of length was the meter. So we did measuring, and I always have the meter stick here in class. Geometry, we did counting. We made it all the way to force. And the unit of force was the Newton. We know the force is a push or a pull. Perfect example of force is always just a weight that you're lifting up, okay? We had the content here. I'll go ahead and I'll do it this way. Same thing basically. So we actually started with measurement and the unit of length. Good. So I just want to put a letter there, L, and we talk about the unit right away. So the unit is the meter. Right? It's the same letter for different things. We've just got to be aware of that. So we did measurements, geometry, etc. The concept of force was very important. We took it just as a muscle sensation. Newton better be capitalized. Speaking of Newton, you guys had some nice pictures of Galileo in your notes. I bought a picture of Isaac Newton as well. I'll try to remember to put that again when we talk about images. So the Newton. And then we found out that work, which is just, I'll use capital W, the unit is Newton times meter because it's a force times displacement. Always remember, lifting something is work, and Newton times meter is the joule. And then we have the idea, I'm just going to write potential energy. Potential energy, we can use the abbreviation PE if we want to, but I'm just going to use the idea that it's stored work, and this energy expression, energy is the capacity to do work. So energy, the capacity to do work. That's not all there is to it, but that's what we're starting with. To do work. Okay. So we're just listing these things. Force, work, potential energy, definition of energy. Love to number things, so I'll number them. Okay. See how far that goes. Okay, one more was power. Power, P is work over time. So those are joules per second, and that is the watt. Okay, so that's power, work per time. And we had already done some discussion of this, the grandfather clock, some other larger scale discussions. But then we saw that we needed the science of motion. So we did a detour here, motion, and we had position, velocity, acceleration, okay, position, velocity, acceleration. And we got out of that, for example, our orbital speeds, which was a pretty nice construction, and which we're going to make use of. So yeah, I'm not going to repeat all of it, but yeah, we had the science of motion there. Free fall plays a huge role. Distance fallen 1/2 gt squared. Finally, we had everything together, all fit there. We had everything together to talk about Newton's law. So Newton's law of motion, Newton's law, and because we needed that, because we had to introduce the mass concept. So mass times acceleration, I'll put vectors on them all, is equal to a net force. So when we got here, we knew about forces and vectors. We knew about acceleration, free fall, motion, and we introduced the mass. So mass, m, right? So not meters in this case, m for mass. The unit is the kilogram. So at this point, everything we've done is expressed in terms of kilograms, meters, and seconds. And well, let me say weight, which is a force, is equal to mass times a particular acceleration, the acceleration due to gravity. So mg, g is 9.8 meters per second squared. We have all that. So at this point, all of our physical quantities reduced to kilograms, meters, and seconds. So all of our physical quantities in terms of kilograms, meters, and seconds. If I ever have to introduce any more, I can always reduce them to this. In particular, energy. So the last thing we arrived at, we've done all this, studied it, the last thing we arrived at was kinetic energy. And because it is an energy, we know it's a capacity to do work, but it's energy inherent in a moving object. Just the very fact that it's moving. So kinetic energy, and we're going to do its definition. Kinetic energy equals 1/2 mv squared. So we absolutely needed this one. And you can imagine it, you know, if you drop a bowling ball on something, after it falls, say 1 or 2 meters, it's going to have enough speed and heft, it's going to be able to drive a nail, it's going to be able to do some work. But I decided to go straight to a really dramatic example, namely an asteroid collision. Because if an asteroid or a meteor, some large chunk of rock coming out of space, strikes the Earth, then it's really going to be a good example of kinetic energy. So that's where we are now. We're imagining an asteroid moving through space. Did I say orbits here? We did the orbital mechanics under motion, so we know how fast roughly these things can move. And what we're going to discuss is this asteroid striking the Earth and developing or blasting out a huge crater. And that's that Arizona Meteor Crater. So next, Arizona Meteor Crater. And I already recommended that you guys go ahead and find some nice images and information on it. And I'm just going to continue the discussion. Right, there's energy and the crater blasted out of the desert. That's the environment. Okay, so we got it all. So Arizona Meteor Crater. So let's start with a picture, and I'm going to do an analysis of this that everybody should be able to follow along with, and we'll turn it into a homework assignment. So we're imagining a chunk of rock, and we don't know exactly how big it is, coming through space, and here's our Earth. Okay, the surface of our Earth. This rock here is headed towards Earth, right? It is going to collide. It's going to collide, so it has kinetic energy up until the instant that it strikes the Earth. Actually, realistically, when meteors strike the atmosphere, so they're still up, you know, some miles, there's a huge amount of friction, and they start to glow and potentially even blow up. Which reminds me, there was a Russian, you guys are going to have to look this one up as well. Over Russia, some half a dozen years ago or so, there was a really dramatic meteor that was captured on a lot of dashboard cameras in cars, and you can find all kinds of videos online. That would be a good one to talk about. Let me put that note right here while it's fresh in my mind. So Russian meteor dash cam. Apparently a lot of people have a camera in their car, and so it was caught many, many times. Dash cam video. I think if you do a search for this, you'll find some amazing footage. While I'm on the subject, so as that meteor crossed the sky and entered the atmosphere, it sent out huge shock waves and broke windows, and all kinds of dramatic stuff happened. So yeah, this is a great tip. So this is actually homework. Watch some of those videos and get some screen captures and print them out. They're pretty dramatic. So watch videos, print out some good screenshots. Whatever suits you. And also maybe, in the case of all of these kind of things, when I send you to find stuff online, get some information about it and write a couple notes down as well, because you're going to put it in your book. So find info, etc. Okay, yeah, that's too good. That's perfect with this topic right here. But here we are, back to our meteor, Arizona Meteor Crater. So we've got the meteor. It's coming in, it's going to strike here. I'll just draw a big star or a big blotch of some kind. And what it's going to do is dig out a crater, literally. Let's see, we'll use black ink for this one. So you're going to end up with a crater, all exaggerated in terms of the size of the Earth. So it's going to dig out that crater. And we know that this thing had kinetic energy is 1/2 its mass times its speed squared. And that energy is going to be transformed into work. So it is transformed into work. What do I mean by that? Energy is the capacity to do work. Well, you try to dig a hole, you know, the size of this Arizona Meteor Crater, which is impressively big, and you'll realize that's a lot of work. You have to lift all the dirt from inside to the outside. Okay? So the kinetic energy is transformed into work, but not only that, plus heat. Now the heat is going to be a thermal physics discussion that comes later in the semester. We're going to do quite a bit about that. But at this point in time, I actually have to at least mention it to you. So that would be thermal physics. And what we will see when we get there, remember the units here are joules, because that's energy, joules. The work, the units are joules, and we're actually going to be able to express heat in terms of joules as well. Like I said, that's a bit off in the future from us, but has to be said right now. So that is the whole theme here, and now I'm going to do a construction. And what I'm going to show you is that based on the size of the crater, we can estimate the size of the meteor. Okay. Now, if I wanted to express this as an equation, I would say, since I said it's transformed, I would say kinetic energy. And by the way, since this is some kind of a sentence here, this is in parentheses. That's what the kinetic energy is. So this sentence says kinetic energy is transformed into work plus heat. Okay. So if I write it as an equation, kinetic energy equals work plus, and we'll use the letter Q for heat. Okay, we'll do that later on in the semester. This equation actually expresses very profound fact. This equal sign, the energy was not lost. Before the collision, we had one kind of energy. It did work and produced heat. Those are other kinds of energy. The equal sign says it's equal. Okay, this much over here, say there were 100 here, equals, you can say 50 plus 50. Okay, that's the idea there. So that's an expression of energy not being lost, not being destroyed, but changing form. So here we're already saying, I said it up here, transform, energy changes form. So that's a little note. Energy changes its form, but the same amount is still there. That's our equal sign. Okay, so now I'm going to do a construction. I'm going to repeat this picture actually on the next board and fill in, after I make a couple more assumptions, then I'll fill in some, turn that into a construction of how big was the meteor. Okay, so let's erase this. Now I got to be a little more systematic and state all of our assumptions. So here's our question. Based on the size of the crater, which you guys are going to look up on the homework, right? You're going to look, if you haven't already found it, you're going to find it. Based on the size of the crater, this is good. Let's try this one. Based on the size of the crater, man, once more we'll feel. Crater, how big was the meteor? How big was the meteor? And here's what we're going to assume. So these are simplifying assumptions. First of all, we're going to say the meteor is made out of the same kind of a rock the Earth is made of. Okay. So one, meteor and Earth material are the same. They don't have to be. The meteor could be made of nickel and iron or something, and the rock could be granite. But we'll just say the same density. Meteor and Earth have the same density. They don't have to be the same material, but we're going to say they have the same density. We're going to let the speed of the meteor, v sub meteor, speed, we're going to make it 10,000 meters per second. That's a very good assumption. The escape velocity from Earth is 11,000 meters per second, so the meteor would actually have at least 11,000 meters per second, okay, at least. However, 10,000 is close to 11,000 is a good, easy number to work with. Okay, so those are our assumptions, and let's draw this picture again down here. One I have up there, a little more, I'll do that right here. So here's the hole that was blasted out by the meteor. And here's the thing, this much Earth had to be lifted out. Okay, so that is a hemisphere of radius r worth of dirt that had to be lifted out. The other assumption is the heat. Now the heat could actually be the greater part of all that energy. Could be the greater part, but we don't know. So we're going to ignore the heat and act as though it was completely converted into work. Okay. That's an assumption that's going to, yeah, it reduces the accuracy, but it's still reasonable because at the moment we don't have any idea of that relation, and this is going to give us a very good idea. Okay, so our third assumption is we're going to ignore the heat Q. So kinetic energy turns into work. That's what we're going to do. Now, 1/2 mv squared. Do this in a couple rows. 1/2 mass of the meteor, v squared, is going to be equal to the work, which is just lifting something. So this is the mass of the crater times g times h. That's simple. That's what we're going to do. Now we have to fill in some unknowns. But by the way, this is the speed and height relation for something just falling down. But you'll notice this is the mass of the meteor, this is the mass of the crater. So it's a slightly different equation than before. Okay, but we are just saying this is the kinetic energy, and this is mgh, lifting something. We've talked about weight times height before. Okay, so let's do this. 1/2. Now the mass of the meteor is the density of the meteor, or just density of the meteor, times its volume, times v for volume, times v squared for speed. Okay. The mass of the crater is the density of the crater, of the Earth, times the volume of the crater. Okay, so capital V volume times G times H, but H is going to be the depth of the crater. Well, I'm going to make the crater, let's call this the Hemispherical Crater. And by the way, this relation here, density times volume, is mass. So mass, I'm using the fact that the density, and that's the Greek letter rho for density, is equal to mass per volume. Density units are kilograms per cubic meter. So I'm just going to keep working on this equation, right? This is a really basic one. Now we have to fill some stuff in. One of my assumptions, by the way, that the densities are the same. Same density means I'm going to be able to cancel the densities from either side. Okay, now we need a little more geometry here. We have 1/2 density and the volume of a sphere 4/3 pi radius cubed. Okay, because that's the radius of the meteor, d squared. And here we're going to have the density of the crater. The volume of the crater is 1/2. It's a hemisphere, so it's 1/2 times 4/3 pi capital radius cubed, because capital R is the radius of the crater. The radius of the meteorite, radius of the crater. And the h, the depth, we're just going to say it's the radius again, because it's a hemisphere. So there you have it. It looks complicated, but what we're going to do is get a bunch of cancellations. And what did we want to know? We wanted to know how big was the meteor. And the size of the meteor is that radius. That's the radius of the meteor. So, by the way, this is a good idea of how a physics calculation is done. Don't be intimidated. We started with a simple idea, and we're just kind of filling in. Looks complicated here. When we're done, it's going to be simple again. Okay. Russian meteor. That's too good to miss. Okay, so what we're going to do now is simplify. And the simplification here, I can do it right here, is pretty nice. Same density means these cancel from both sides. Okay, the 4/3 are canceling. The 1/2 are canceling. How great is that? Pi. Not that much left, is there? So I'm going to divide both sides by b squared, and we'll be done. So what we're left with here is radius cubed of our meteor. Everything else canceled. Did I cancel pi as well? I wanted to. Pi. Okay. So what do we have? Radius cubed. This is being divided, so I cancel on the left side. Is going to be. Oh, I missed a letter. I missed the letter G. G had to come down here as well. Make sure I didn't miss anything else. Rho, B, G, H was turned into R. So that's good. So depth equals radius. Now we're ready to go. So radius cubed is equal to radius to the 4th g over speed squared. Now this is an estimate, but you guys are going to see that it's a pretty good one. We have to check the units. So radius times g, length squared over time squared, length squared. Yes, this is a good expression. Where r equals radius of the meteor. Capital R is radius of the crater. G equals 9.8 meters per second squared, and V equals 10,000 meters per second. So this is a homework, but I'm actually going to do it later, but I wouldn't mind everybody give this a try if you have the calculator. The final answer, we have to take the 1/3 power, or the cube root. So R is equal to, I'll write the G first, R to the 4th divided by V squared to the 1/3 power. And it's been a while since I did this, but I had tried this and looked up the Arizona Meteor Crater, and this basic calculation gave a pretty good estimate compared to what the so-called experts, what they claim. And why shouldn't it? The experts are also just using physics, so we'll get a pretty decent result right here. So here's part of our homework, and let me add homework here. So Arizona Meteor Crater, what you want to find is the diameter, and therefore the radius, right? You want to find depth, so you get those data, and estimated size of the meteor. And we'll compare it to our own calculation here, which is pretty good. I want to say one thing about the depth here. The depth is, in the real meteor crater, it's quite a bit shallower than the radius, but that's because it's filled with a lot of rubble. So when the meteor blasted that crater out, a lot of the rocks went up in the air and fell right back down in. Okay. So it's a reasonable assumption, that the amount of work done is the radius, is the height here. Okay, it's a reasonable assumption. So when you use, for this radius here, you use half of the diameter of the meteor crater. Okay. Put that in there. So that's fine. And then finally, calculate star here. I always name everything star if you can, and I'll go and calculate it too and share it with you guys. So homework, we want pictures and information. We want pictures of these things. Put those in your book. Let me consult the clock now. Yeah, this is a great project for this part of the semester, because it took a lot of doing for us to be able to discuss this thing. And yeah, I know I'm trying to turn you into professional physicists, but always take a problem like this from the easy part, right? You realize the rock just blasted in there and lifted the dirt out. We know kinetic energy and we know work, so this here shouldn't threaten you, right? As we go down here, it gets a little more intense, but just leave a lot of space, copy everything down, and just work it to your best of your ability. I'm not expecting you to be able to do this during an exam, okay? But it'll be a nice one to pursue, and like I said, you can get all these interesting pictures and various informations, put them in your book, print them out, put them in your book. This Russian meteor dash cam video, that should bring some interesting stuff up as well. If you haven't seen it before, I think you'll be pretty interested in what that looks like when it crosses the sky. It was by no means as big as this monster here, okay, but it's still pretty intense and interesting event. Okay. What I'll do now, since this kind of closes off the topic, check the clock again. Yeah, I'm just going to set up what we're going to do next time. is definitely a good project that's worth pursuing. And if you have specific questions about these types of calculations and how to do this on your calculator, go ahead and email me and let me know. So I'd be glad to address this again. A lot going on here. The 10,000 meters per second I talked about earlier, that's comparable to the 7,900 of the orbital speed that we calculated ourselves. And a meteor will actually, from outer space, will actually come in with greater speed than the orbital speed. So it's a good number, good number. Okay, so what I'm going to wrap this up with and set up for next time, our topic now is something called conservation of energy. And this meteor crater discussion was an example of it. So next time, what's called conservation of energy. And it's a law of conservation of energy. It says energy is neither created nor destroyed, it changes form. And this is what we had with our meteor crater. We had kinetic energy, it dug a hole, produced a lot of heat that we don't know about yet, so the energy changes form. Conservation of energy. Energy changes form, but it is not created or destroyed. It's always changing its form. So that's going to be a really important central topic of the entire semester. What else do I have for you here? Conservation of energy. Oh, there's one thing that was on my agenda about this blast. Okay, so this meteor crater, here's our speed. If the speed is 10,000 meters per second, and the crater is, let's just exaggerate, let's say it's 1,000 meters deep, okay? Now 10,000 meters per second, 1,000 meters deep, that means that meteor came to a stop in 1/10 of a second, roughly, okay? That is a short time for a house-sized rock to just come to a stop, and that's why so much explosive energy is released. We'll come back to that. That just came to mind, okay? Because you're wondering, why does the thing make such a big explosion, which you're going to see on these guys? It has to do with the speed with which it happens. Okay, but let's leave it at that. This is a good topic. Hope you guys enjoy looking some of these things up. Give this thing a try. Compare to the compare to the official data, right? You're going to get the official data, what the Meteor Crater website says, and then you can compare that to your calculation. Good. See you guys next time.